There's one sometimes unintended side effect that can happen when we have a stereocenter next to a carbonyl, and that is because of the keto-enol tautomerization. Even though the ketone form in this example of a ketone, the keto form is the predominant form, some of the molecules are going through keto-enol tautomerization. So part of the time, this molecule will be in the enol form, and due to that, we'll lose stereochemistry at this carbon. Because now, as it goes from the enol back to the ketone, now this methyl group can be either coming out or going back. And so now we have a racemic mixture of our two enantiomers. If we allow this to equilibrate long enough, so we start with a ketone, we form a small amount of the enol, then it forms either the same ketone we started with or it forms the opposite ketone. Then those molecules can then form the enol, can reform the ketone, can reform the enol, can reform the ketone, and as it does that repeatedly, eventually we're going to get to a point where we have a racemic mixture because there is no preference for one of these ketones versus the other one as far as the stereochemistry goes. In section 23.7, we'll look at halogenation of the alpha carbon, and we can either do acidic halogenation or basic. So I'll start with acidic, and we'll talk about the mechanism of the acidic halogenation, and then we'll go through a basic halogenation as well. So as always, the normal questions arise: who has electrons, who wants them? The proton definitely is going to be who wants them. If we treat a ketone with acid, we can protonate the carbonyl oxygen. And then water or something else from the solvent can come by and deprotonate to form our enol. So that's just a keto-enol tautomerization. But now once we have the enol, that can react with our Cl2. And now the mechanism, while similar to what we've seen before, is slightly different. The electron pair from the OH comes down to reform our carbonyl. This electron pair from the enol comes out and grabs one of the chlorines, and that chlorine leaves to give us our intermediate. We've added one chlorine to our molecule now. However, our second chloride comes by and deprotonates our protonated ketone to get rid of the positive charge. And in effect, what we've done is we've substituted H for chlorine at the alpha carbon. Now we can do that same thing in basic solution, although now instead of using an enol, we'll use an enolate. And here the hydroxide can come by, deprotonate this to form the enolate, which then can react with our Cl2. The electron pair comes back down and reform the carbonyl. The electron pair from the enolate comes out and grabs the chlorine, and that chlorine leaves. And once again, we've halogenated at the alpha position. Now, one issue, however, with this reaction is that we still have more hydrogens that are in alpha position, and this reaction can keep going because actually this hydrogen is now more reactive than the one was back here with the extra chlorine on there. So now this reaction can continue, and my base can pull off another proton, which can come over and form a new enolate. That enolate can react with another molecule of chlorine. Electron pair comes back down, reforms the carbonyl. This electron pair comes out, gets chlorinated. That chlorine leaves. And now I've added two chlorines to my molecule. Now, a great synthetic use of this is that if we have something like cyclohexanone, especially something that's symmetrical, so there's only one place that we can react, and now if I treat this with some kind of base, it doesn't even have to be that strong of a base, like lithium carbonate, for example, and lithium bromide and DMF. DMF is dimethylformamide, or NN-dimethylformamide. That's DMF. It's just a good polar aprotic solvent. This is going to be a strong enough base to deprotonate this and remove HBr, because what we get is an alpha-beta unsaturated carbonyl. So this alkene is especially stable because it's in conjugation with the carbonyl. Another reaction that we can do alpha to the carbonyl is that we can do an alkylation. Of course, carbon-carbon bond-forming reactions are very important. So if we react our cyclohexanone with LDA and THF, we can make the enolate. And then if I take that enolate and react it with some kind of an alkyl halide, in this case chloroethane, I go back to the same things that I've always been doing, saying who has electrons and who wants them. Who wants them is going to be the carbon that has the halogen on it. Remember, halogens are great leaving groups. And then who has the electrons is a little bit complicated, because we can look at the alkoxide and see that we think that the alkoxide has them, but if you remember the way that we've been reacting our enolates, it really ends up being this carbon here who has our electrons. So this electron pair comes back down to reform the carbonyl. This electron pair comes out, and it's this carbon here what it's going to attach to. This comes out to the carbon that wants electrons, and the halogen leaves. And what we get is we get our new alkyl group alpha to the carbonyl. And the carbonyl is still there, so if we want to do other chemistry with the carbonyl, we still can. We can now use our alpha substitution reactions and our understanding of kinetic versus thermodynamic properties to put an ethyl group on the more substituted side and put a propyl group on the less substituted side. So this would be your thermodynamic reaction. This would be a kinetic reaction. So go through and try to figure out how to do that, and then come back and I'll walk you through it. So if you're going to put both of these groups on, it's going to be important to react first at our thermodynamic position, because if I put the kinetic alkyl group on first, then I'll have two tertiary hydrogens, one on each side of the carbonyl, and that will make the second step much more complicated. But if I react first at the more substituted position, we get the methyl and the ethyl both on here at the same time. Now there are no hydrogens here to substitute, and I can do my other reaction on the other side pretty easily. So if I want thermodynamic conditions, then I want to have a good base that is reversible. So I will use sodium ethoxide in ethanol. I want it warm, so room temperature. And ethanol is my polar protic solvent. That will cause equilibration to give the more stable enolate. You don't necessarily have to draw this as a separate step. At least in a synthesis you wouldn't have to. Which then we can react with chloroethane to add the ethyl group to the thermodynamic position. Now you could have also written that in one arrow with 1 sodium ethoxide and ethanol at room temperature, and 2 with chloroethane, and write that really as a single reaction step. Then once we've done that, now we can actually use any kind of base, because now there is only one alpha hydrogen left. There are 2 hydrogens here, but there's only one position. So now I can treat this with LDA in THF, LDA being a strong base. And the temperature actually doesn't really matter, but oftentimes we'll do it at -78 if we're trying to get a kinetic enolate. And 2, I'm then going to react with propyl chloride, or propyl bromide would work as well, to put the propyl group on in the alpha position, and that will get us to our product. So it's only 2 or 3 steps depending on how you view it.